So for this last lecture of today, I'm going to just talk about some of the recap, sort of what we've learned about turbulence, some of the main points that I want you to take away conceptually about turbulence. So the first thing is what determines whether it's turbulent, and that's very important. It's the Reynolds number. And the Reynolds number, as we know, is a ratio of inertial force to viscous forces. And when the inertial forces get large enough relative to viscous forces, that's when turbulence occurs. So viscous forces tend to prevent turbulence. The flow is sticky. It's not, it's not soft, and it's not easy to flow. It's harder to move if it's got high viscosity. But if it's got low viscosity, then it's easier to move and it's less stable to this kind of turbulent flow. And of course, inertial effects increasing as the speed goes up. So this Reynolds number is a ratio of inertial forces to viscous forces. And when that ratio gets high enough, we see turbulence. So it's always the Reynolds number that's determining whether or not it's turbulent. If the Reynolds number is greater than about 100. This varies from like 30 to 200 depending on the exact situation, but this is a general criteria that is applicable to many types of flow, for flows where there's an obstruction or a free jet. So either of those two situations, this condition is a pretty good approximation for when you're going to see turbulence. It's not precise, but it gives you a basic idea. If you've got a Reynolds number that's 1,000, you're definitely going to be seeing turbulence. If you've got a Reynolds number that's 1, you're probably not going to be seeing any turbulence in a flow like that. For flow over a plate, the criteria that we've learned is 5 times 10 to the minus 5th. And we've seen that that's because it's so large compared to this 100, because that's not the obstruction to the flow. The thing that's obstructing the flow is actually the slow-moving liquid in the boundary layer, and this dimension, this L, is not that scale. This scale is the scale of the length of the plate, which really isn't obstructing the flow at all. So this position is when the boundary layer actually becomes big enough to induce turbulence, and that's what's really causing it. But nonetheless, this Reynolds number of 5 times 10 to the 5 is the accepted transition point for turbulence and flow over a plate. When you have flow in a pipe or a duct, we see that turbulence tends to be suppressed because the walls of the pipe or duct, of course, prevent turbulence to some degree. They stabilize the flow. And the general rule is Reynolds number based on hydraulic diameter of 2,000 or greater, and you will have turbulence. The hydraulic diameter for a circular pipe is just D. So in the case of circular pipes, it's just Reynolds number based on diameter is greater than 2,000 for that transition. Another important point is that turbulence is always unsteady and three-dimensional. And this is a point that sometimes gets lost because we do talk about time average behavior. And it's tempting for some people to stop remembering that the turbulent flow in its real form is always swirling and churning in 3 dimensions and is never truly steady. It's never steady at all. So turbulent flow is never steady and is always 3D. But we can look at it and talk about it in terms of 2D and in terms of steady time average behavior by using time average velocities, which we symbolize by U and V. Turbulence increases friction relative to laminar flow. So if you look on the Moody chart, that's very obvious. If you look at this chart, you can see that as you go to higher Reynolds numbers along the laminar line, friction factor is dropping, and then when it becomes turbulent, it jumps up here. So you see this clear increase in friction factor when you go from laminar to turbulent. That is what turbulence always has more friction relative to a similar laminar flow, because you have that swirling motion that brings fast-moving liquid into contact with walls or objects that are near it. This is evident in the formulas we looked at when we looked at the momentum equation, when we looked at the time average momentum equation. This was evident because the term nu was replaced in the viscous force terms with nu plus EM, epsilon M. Epsilon M is the momentum eddy diffusivity. So we see that the effective viscosity of turbulent flow is simply greater than the real viscosity of the flow. So turbulence essentially adds a type of viscous-like effect to the flow. This is always a model thing you have to model. These models are always determined empirically. All turbulence relationships are empirical. Empirical means determined by experiment. So none of the models that are really that give us correct relations of turbulence, none of them is free from experimental correction. Some of the models, get us close. If you get into go to graduate school, you'll study perhaps turbulence modeling, and you can see some of the models. But at the end of the day, even if they're based on some sound physics, they have to rely on experimental evidence in order to close the loop, as it were, and come up with actual useful engineering relationships for turbulence. In pipe turbulence, there are two major effects aside from increasing friction. We know it increases friction. It also decreases the entrance length. So we saw a significant decrease in the entrance length before the flow becomes fully developed if you have turbulence. So for turbulent pipe flow, usually the entrance length is quite short. It also makes the flow velocity profile more uniform. So we saw in the last couple of lectures that turbulent flow velocity profiles do not have the parabolic shape that we saw with laminar flow. And in fact, they more closely resemble slug flow, where the flow is truly uniform in turbulent flow. It's not exactly uniform. It definitely is not quite uniform, but it's more uniform in a time average sense than the flow in laminar flow is. So we can use approximations of flow uniformity with more confidence if you have turbulent flow than if you have laminar flow. Finally, if you have flow over plates, the turbulent boundary layer grows almost linearly, we saw, which means if you're looking at flow over a plate, you'll see a region with a slow growing x to the 1/2 growth for laminar flow. Then when it becomes turbulent, that boundary layer tends to increase pretty dramatically relative to the laminar portion of the flow. So turbulent boundary layers tend to be, grow much more quickly. They grow at an x power of almost x to the 1 power rather than that x to the 1/2 power that we were able to prove that we saw for laminar flow. But again, all of this is based on empiricism, looking at turbulent flows and seeing what they do, because everything in turbulence ultimately boils down to experimental relations.